This will be a more or less unconclusive video about switch mode power supplies. I don't pretend anything. I even don't want to pretend how they all work. I only take a few basic conclusions about switch mode power supplies, and there are more videos on YouTube of which you can learn much more anyway. Only a demonstration of the problems. This is one of these power supplies. The good thing of these power supplies, they are small, they don't weigh too much, there's not a heavy transformer inside, like this, heavy transformer. But in fact we don't know much about the working principles. And even when, for instance, you look at such an extremely small switch mode power supply, travel adapter, you don't know what's happening inside. The only thing that we know is that AC gets in and DC gets out, and often for many simple computer things it's 4.5 volts or 5 volt anyway. So what happens inside here? To know what happens inside, you have to open it. That's the first thing. Then take your oscilloscope, measure what happens, and measure at the output with a dummy load that gives a nominal voltage that the circuit can give. Say it's 500 milliampere at 5 volts, and with Ohm's law you can calculate when that current flows. Connect an amperemeter in the positive lead. We don't know of all these beautifully made switch mode power supplies whether they generate high F noise, high frequency noise, and I'm absolutely sure they do. All these circuits give a lot of noise, but all this noise is within the specifications that the European Union or America or whatever country tells us that's good. They give noise anyway, it's within the specifications. When you stick such a thing into your in the wall, it also will generate noise in your whole wall wiring. I hope that is the good word. All the wiring in the house can be influenced by a bad, not properly made switch mode power supply. And shortwave listeners and radio amateurs often hear a lot of noise generated by all these circuits. Anyway, let's throw it away. Not only because of that. By the way, you can use it for a Christmas tree. That's very useful. You have to take in account Ohm's law, and then you can connect many LEDs or the Christmas tree light bulbs to it. Very easy. And you can charge the battery with it. I've done that here. Making a to charge a battery, nickel cadmium battery, with the help of such a switch mode power supply. That are all non-critical applications. So again, I want to say I don't pretend anything with this video. So this is a black box, the switch mode power supply. But what we do know, that there is an oscillator inside. And what do we know of an oscillator? Here are the most important phenomena of an oscillator that changes AC here into DC. It works on 100 kHz, 60 kHz, you even don't know. And perhaps when you open it, perhaps there's no oscillator inside. In that case you have to search how the circuit works. Perhaps there's a bridge rectifier with a resistor or whatever that and a resistor that drops the voltage, etc., or an intelligent chip that does the same thing. Could be. But in general, for the bigger switch mode power supplies, there is an oscillator inside. The classic phenomenon from an oscillator is that the frequency can change depending on the load. And that's also the reason why in many of these simple power supplies the current switches off when the current is too high. The switch mode power supply switches off. So there's an intelligent circuit inside that switches the current off, because otherwise the whole thing will start to smoke, etc. And there's often a fuse inside, but I've opened many of them. Sometimes there's even no fuse inside. Be aware of that. And these oscillators are often made to generate square waves, and that's what we know of square waves, that square waves have a lot of harmonics. So you will find at the output of such a switch mode power supply, perhaps, don't know that, it depends on the filtering, a lot of harmonics. In general, they perhaps they make a sine wave, but it's reversed or changed into another wave to get a DC out. Here we have a DC out with a certain current, say max 10 ampere or so. And the harmonics can differ, and that depends on the load. That has all to do with the quality of the switch mode power supply. When a big current is taken out of that supply, it could be that it gives out much more harmonics and more or less irregular, undefined noise on a high frequency. So you don't know what kinds of noise such a circuit can give. So broad spectrum high frequency harmonics can occur, especially with not properly designed switch mode power supplies. So high frequency filtering is always necessary. There is, of course, inside such a power supply, in general, there is a filter, there's filtering inside. Often they use a P filter, but also other kinds of filters, and all these filters are specific. They are made specific according to the whole setup, the electronic setup of the switch mode power supply. So there's nothing to say in general, though I want to go more or less to general ideas and solutions to make such a things usable anyway. You have to know what the whole thing does, but I've talked about it earlier. There are also regulator issues. How good does the switch mode power supply work when the when the current here goes in an irregular way? So a lot of current, and on the other moment a very small current. It could be that the regulator is not able to regulate that properly without generating harmonics. That's a classical problem with oscillators. So back to the P filter. This is a kind of simple solution, a kind of simple idea how you can make a filter for it. But of course, according to all these issues, there is no guarantee that this works. And anyway, We send in here the 110 230 volts AC, 50 Hz, 60 Hz. This is the black box. And we can use here a filter, that's the first idea, to switch out all kinds of... You can find these filters in computers. Perhaps, I don't know that, in that black box there is already such a filter. But for extra safety, extra effect, could be that you can make such a filter, use such a filter. They often are made in this way. All these capacitors, good ground, all these capacitors have to work on very high voltages, say 600 volts or so, non-polar capacitors in the range 4 and 7, 4700 4700 picofarads. That's an idea, a filter. And here's the black box out. When you see these kinds of noises, irregular noises on your oscilloscope, when you connect it to the output of the black box switch mode power supply, you have a big problem, because they are so irregular. So how to filter out these irregular harmonics? And in the earlier video that I've made, there are bursts here. So a burst, suddenly it stops, a burst, it stops, all kinds of bursts. And for audio that will be a big problem. When you will hear these bursts when you connect the switch mode power supply to an audio amplifier. You will hear these bursts, absolutely. And they can mix in with the frequencies that the audio amplifier has to amplify. Say it amplifies 10 kilohertz and the burst is on 20 kilohertz. You have a mix. You can get a mixing frequency that you will hear in your loudspeaker. So this is a poor man's solution. It doesn't pretend anything. It does not pretend that you can solve the problems with this black box, switch mode, etc. But this could be an idea, a P filter, a resistor, another P filter and another resistor. And could be that approximately 70% of the noise and the idiot bursts do not appear any longer. But of course the whole circuit has to deliver a certain current, so these resistors cannot be too high, unless you have here a circuit that doesn't take any current, a few milliamperes or so. Could be when you have a high frequency preamp that takes 3 milliampere or 10 milliampere. Sorry, high frequency preamp, an audio preamp that takes 3 milliampere or 10 milliampere. Could be that this works. Then you can make the value of these resistors higher. That gives a better, a better smoothing out effect. You can also experiment with different ferrite materials for the filters. All these ferrite materials have certain properties, and you can sometimes find their properties by the color code. And you can see here yellow ones. They are made for a specific frequency band. That's an idea. And here we have other ferrite materials. So when you salvage a lot of ferrite materials, a good idea to do some experiments. The capacitors here, you have to find them out experimental, because I don't know the frequency from the switch mode power supply. In general, you can start with 100 nanofarad. That's in general a good value, but perhaps you have better results with 4 0.7 nanofarad or 50 nanofarad. Do some experiments. Of course, connect your scope here to the output, then you can see everything that happens in the circuit. And what also can help is this very small value capacitors in the 1 nanofarad up to 4.7 nanofarad range from the positive lead to the shielding. Such a power supply, it strays out a lot of frequencies, it's unshielded, so mount it in a metal box, and especially from tin plate, steel, the wiring to the outside, and then from the positive to the negative this filter, and then small capacitors to the outside, to the tin plate where the whole thing is built in. I had very good experience with that. I once had a satellite receiver of which the whole logic circuit got deteriorated by the burst on the switch mode power supply. So all the channels went away. When I switched from channel A to B, it didn't work. But when I mounted very small capacitors from the positive of that switch mode power supply to the tin plate shielding, I could damp out all the noise, and it worked properly. And also here, from the negative to the shielding, you can use small value capacitors in the 1 nano up to 4.7 nanofarad range to get out all of the noise, disturbing signals, etc. out of that switch mode power supply. Well, that was all to tell. You can of course experiment with more and less windings. I don't give solutions, I only give ideas. Perhaps this will work. Small capacitor from 4.7 nanofarad, then you know that this frequency gets more specific. You get a kind of bandwidth to the frequency to which this P filter works. So, a lot to experiment, a lot to do, only ideas. Don't shoot me down on this video. So here is that circuit again, what I've told. You can see on the scope that DC and AC are on the same lead, power supply lead. And of course, when the disturbing frequency has a very pure waveform, it's a square wave or a sine wave, it's easier to damp it out, because you can take profit of the fact that you know the exact frequency